Hi everyone, and welcome to the first Unity lesson for .NET Professionals. This lesson will be dedicated to computer graphics, and here I will try to explain how the geometry is getting rendered. So here we have Autodesk Maya, and let's create a simple cube. It consists of vertices, edges and triangles. We cannot see triangles right now because Maya simplified the geometry in order to make it more simpler to work with. So let's make Maya display them. The basic building block of any geometry is vertex. Vertex is a simple thing that has some attributes. The first attribute is vertex position, which defines the position of vertex in local space of this model. The second attribute is color, and you can define with your shaders how to use it. The third attribute of vertex is UV coordinate. The UVs are used to project two-dimensional texture into three-dimensional space. Each vertex has its own coordinate in UV space, which is bounded into square with sides of one unit. The fourth is normal, which defines the orientation of vertex in space and is used, for example, to define the visibility of triangles, so-called backface culling. So, the geometry has to pass several graphics pipeline steps in order to appear on user screen. For deeper understanding of each step, please refer to Render Help book by Simon Trappler, followed by the link below. Within this lesson, I will cover most important parts of rendering process. The first step is input assembly. At this step, CPU combines vertices into vertex buffers in specific order, so the graphics card could understand how are they connected to each other to make triangles. Then comes the second, vertex shading stage. At this stage, vertex positions are transformed from local space to so-called clip space, the space of the camera frustum, as can be seen on the picture. Model view projection, or MVP matrix, is used to transform vertices. As for example, Unity does this in vertex shader when multiplying vertex position by built-in Unity matrix MVP variable. Then, vertex attributes have to be interpolated. This is done so the graphics card could understand what's going on in between the vertices, because before interpolation all the GPU has is a set of separated vertex structures. So let's look how interpolation works on the example of colors and normals. At first, let's paint some vertices in different colors. This one will be red, this one is blue, and another one is yellow. This is how the cube looks like after colors interpolation. Anyway, in order to see vertex colors of your mesh, the shader should take them into account. Now let's see normals interpolation. As you can notice, each vertex has 3 normals. But that is not possible, since every vertex can have only one. What is actually happening is that Maya makes 3 copies of vertex, so they would have different normals, and show them as one. See this sharp edge here? This edge is the reason for such manipulations. Let me show you what happens if we merge those virtual vertices. Here we softened all cube's edges, so Maya merged every 3 virtual vertices into one, and averaged their normals. You can see how Maya tries to shade the cube according to new normals, which are now smoothly interpolated along edges from one to another. So now cube behaves more like a sphere. In Hypershade window, we can see that our cube uses Lambertian lighting model, which shades the geometry according to how its normals are oriented to light direction. Let's get it back to normal. So now you can see how the colors and normals were interpolated, and now GPU has a little bit more information about how to display the geometry. Next comes the fragment shading stage. The geometry is rasterized into fragments, and now GPU refers to fragment shader in order to shade each one of them. Here the lighting and textures are combined to calculate the final color of each fragment. At last, rasterized geometry is sent to frame buffer, and after some final calculations it gets to the screen. Anyway, there are even more stages in graphics pipeline which are optional. For example, iteration stage, which generates even more vertices than was originally sent to GPU, to make smoother and more detailed geometry without affecting the amount of operational memory used by the mesh. So this is the basic of how the graphics pipeline works. Now I hope you have a deeper understanding of the geometry you're gonna work with, what parts it consists of, and how it is transformed when getting from model to the screen. Thank you for your attention. Don't forget to leave your questions and comments, and of course subscribe to my channel. See you soon in the next lessons.